Welcome to the University of Hawaii Vertically Integrated Project, Drone Technologies Technical Design and Flight Readiness Review. UH Drone Technologies consists of 36 members, all separated into various UAS subsystems. Before we begin, here's a brief introduction to the competition team.
Hi, my name is Cameron Jamila. I'm a third-year mechanical engineering student. I've been a part of UHDT for 3 years, and I'm the project manager.
Hi, my name is Kai Merchant. I'm a fourth-year mechanical engineering student. I've been with the team for 2 years now, and I'm the air delivery subsystem lead.
Hi, I'm Leolani Rodriguez. I'm a third-year mechanical engineering student. I've been with the team for 1 year, and I'm the co-lead for the air delivery subsystem.
Hi, my name is Milo Higa. I am a fourth-year senior majoring in mechanical engineering. This is my first year on UHDT, and I am part of the UAV hardware subsystem.
Hi, my name is Gavin Ng, and I'm a third-year computer engineering student. This is my second year on UHDT, and I am the IP subsystem lead.
Hello, my name is Ethan Golnak, and I'm a fourth-year mechanical engineering senior. This is my first year on UHDT, and I am part of the UAV hardware subsystem. I'm also this year's team captain.
The purpose of UHDT is to create an autonomous unmanned aerial system, air delivery system, and autonomous image processing system that successfully performs all expected obligations of the 2023 SUAS competition. With that said, we will now go into the technical design UHDT has developed for this year's SUAS competition. UHDT consists of 4 major technical subsystems: unmanned aerial vehicle hardware, unmanned aerial vehicle software, air delivery, and image processing. From the 2023 SUAS competition rule set, UHDT has developed functional requirements for all subsystems. First, for the UAV hardware subsystem, the subsystem shall ensure that no parts of the drone shall depart from the aircraft except for appropriate air delivery parts and modules. The drone shall be capable of heavier than air flight and also house and lift all necessary components for the mission. The drone shall be able to fly 12 miles under 30 minutes as laid out by the mission timeline. The UAS must able to operate in 15 mile per hour winds with gusts up to 20 miles per hour, while maintaining an altitude between 75 and 400 feet above ground level. The aircraft must be capable of autonomous takeoff and landing on pavement or grass fields. We also want to ensure that the drone can safely take off and land without damaging the aircraft. The software subsystem must ensure the entire flight is autonomous. Therefore, it is crucial for software to input the correct sequence of waypoints so the drone can successfully fly within 15 feet of each waypoint. At the competition location, there will be a mission flight boundary. Therefore, it is important that the sequence of waypoints does not go outside this boundary. When the UAS is more than 200 feet away from the runway, there is a minimum height requirement of 25 feet above ground level. There is a deduction of points if the UAS were to crash. Therefore, it is important that the UAS has a way of avoiding other drones. To avoid crashing into other drones, the pilot will maintain constant line of sight. And if a crash is about to occur, the pilot will take over manual control and avoid the crash. For IP, as per the updated guidelines, airdrop locations are no longer known in advance and must be identified through object detection, classification, and localization. The IP subsystem must develop algorithms that ensures the drone autonomously detects targets, classify targets by color, shape, and alphanumeric, and geotag targets. The algorithms were tested against the fixed number of valid shapes and colors outlined in the competition guidelines. UAV hardware, the subsystem responsible for developing an aircraft, is an essential component towards the entire system, as without a robust and reliable drone, we would not be able to complete the mission. The subsystem works to develop an airframe and propulsion system that will be able to house all components from all subsystems while maintaining the performance metrics set by our requirement. The software for the UAV consists of 2 Python scripts, waypointnav.py and payload.py. Waypointnav.py is for waypoint navigation and to provide a search pattern for the air delivery area. The coordinates of the waypoints and search pattern will be manually inputted and then converted into a waypoint file for the UAV to execute within Mission Planner. After searching the air delivery area, the second script, payload.py, will obtain the target's GPS coordinates from the object detection, classification, and localization script. and then create another waypoint file to fly back to the corresponding payload target. Once all payloads have been safely delivered, the payload.py script will signal the UAV to return to launch, completing the mission. The air delivery mechanism operates autonomously in conjunction with the image processing scripts. This script signals a servo motor connected to a pin, which releases a single water bottle payload. This is released from the underside compartment of the drone. Once the payload is released, a radial damper and line allows the payload to safely and accurately lower onto the target. Once the payload touches the ground, the remaining line unspools from the UAV. The UAV can now continue to the next payload location. The object detection, classification, and localization system consists of 4 main algorithms: object detection and shape recognition, geotagging, color recognition, and alphanumeric recognition. Image will be passed through each algorithm one at a time, with the results of each algorithm being passed to an intermediate processing function or the next primary algorithm. After the images are processed through these 4 algorithms, they are checked against common errors due to similar characteristics by running them through close enough test cases that use the targets on the payload labels. The GPS coordinates of the identified targets are then sent to the UAV's payload.py script for waypoint creation and drone navigation. The drone is equipped with a Sony a6400. This camera has a 24 megapixel APS-C sensor capable of taking 4K images with a resolution of 6000 by 4000 pixels. The camera is also equipped with a real-time tracking autofocus, in-body image stabilization, and an anti-vibration lens to produce clear images. The object detection and shape recognition algorithms take images from the drone's camera and returns cropped images of the targets. It uses the YOLO v5 computer vision model. The algorithm takes features from input images and feeds them through a prediction system which draws boxes around detected objects and predicts their shape. The output of the object detection and shape recognition algorithms are then passed to the geotagging algorithm, which calculates the detected object's coordinates by passing sensor data such as the drone's GPS coordinates, altitude, heading, pitch, and roll into a series of formulas. The color recognition algorithm determines the average amount of space that the target's background shape and letter will take. The algorithm uses k-means clustering to make inferences by grouping similar data points and finding underlying patterns. In this algorithm, each of the 10 competition colors represent a cluster. The algorithm previously used RGB for its color model, but was transitioned to HSV for increased accuracy. After the target images have been complemented and filtered for noise using the results of color recognition, they are then processed through the drone's alphanumeric recognition algorithm. This algorithm uses Google's Tesseract OCR engine as its base, and was trained against hundreds of images of alphanumeric characters at various rotations. Before implementing the Python script for UAS autonomous flight capabilities, another option was considered. This required MATLAB and its generated waypoint files to search the area. MATLAB was not selected since there would have to be a second script for waypoint navigation running in parallel with the MATLAB generated waypoint file for searching the area. Python allowed for one script to be used. Due to a larger number of libraries and capabilities, Python was chosen for UAS. MATLAB was previously considered for the algorithms in the ODCL system, but was replaced by Python for several reasons. Mission Planner only executes Python scripts, and Python offers a greater degree of flexibility with a larger number of available libraries. Previously, a faster RCNN algorithm was used for object detection and shape recognition, but since then, the algorithm was replaced with a YOLO v5 algorithm due to its faster speeds and higher accuracies. There are 2 risks that the UAV hardware subsystem has identified. The first risk is a crash due to the arms or motors rotating during flight with a likelihood of 4 and a consequence of 5. It was discovered that even if the arm clamp screw were tight, the arm could still rotate if a significant torque was applied. The arm clamp screws are currently tightened to a torque of 8 inch-pounds. The arm clamps cannot be tightened too much because it will cause the carbon fiber arms to crack. Also, if the screws on the motors or arm clamps loosen during flight, it could cause the motors or arms to rotate. The mitigation for this risk was to use thread lock on the screws, apply a friction paste to the arm clamps, and pin the arms and motors in place with set screws. The second risk is the UAV not having enough flight endurance to complete the mission with a likelihood of 3 and a consequence of 5. The quadcopter's flight endurance was estimated to be 15 miles based on the hovering power draw, which would be more than enough for the mission since the minimum distance required is 12 miles. However, the power consumption will be greater for the thrust required for cruise speed compared to hovering, which would decrease the flight endurance. The flight mitigation for the risk would be to perform flight tests in order to gather data on the flight endurance and power consumption of the UAV. We could also implement larger batteries if the tests conclude that the additional energy is needed. UAV software has identified 2 risks. The first risk is if the Python script fails and crashes. This could happen due to a faulty script, and it has a likelihood of 2 and a consequence of 5. We can mitigate this risk by running software-in-the-loop simulations, in addition to using Mission Planner and Google Earth Pro to check for bugs in the script. The second risk we identified is if the waypoints are inputted incorrectly. This is a possibility due to human error in the transferring of the information from the competition sheet into our script. This risk has a likelihood of 1 and a consequence of 5. To mitigate this risk, the Python script will allow for a re-input of waypoints after the initial input. This will allow us to double check that the first coordinates were inputted correctly. The air delivery subsystem has detected 2 different risks which might impact the mission. The first risk is the release mechanism failing. This can be caused by a servo motor malfunction or a component being jammed in flight. This risk has a likelihood of 2 and a consequence of 5. This could lead to payloads not dropping and deducting points. To mitigate the risk, the air delivery subsystem has conducted flight tests with the UAV to ensure that the servo motors function properly and drops the payload at the correct time. Another risk is the fishing lines becoming tangled, causing a jam or free fall of the payload. This risk has a likelihood of 2 and a consequence of 4. If this occurs, it could result in a failed air delivery attempt due to the payload not being delivered or the payload being damaged. To mitigate this risk, air delivery will ensure that the lines are not tangled during assembly and pre-flight checks. The image processing subsystem has identified 3 possible risks. The first risk is that the ODCL script being unable to detect some of the standard targets. This could happen if the object detection algorithm is insufficiently trained. The IP subsystem is planning to mitigate this through frequent testing and improving the dataset used to train the model. The second risk is the ODCL script being unable to classify some of the targets or misclassifying non-targets. This could happen due to the lighting in the pictures or background features having similar characteristics to the targets. The IP subsystem is planning to mitigate this risk through the implementation of close enough cases, which will take advantage of labeled payloads. The last risk is the system being unable to save pictures or transfer them to the algorithms. This may happen if the hardware, software, or code is incapable or not configured to live transfer images. The IP subsystem is planning to minimize the risk by periodically testing changes to hardware, software settings, and our codebase where necessary. That concludes University of Hawaii Drone Technology's Technical Design Review. We will now go into showing why our UAS is flight ready. Images with a resolution of 6,000 by 4,000 pixels were passed into the object detection and shape recognition algorithm. These algorithms are able to detect 98.3% of the targets in 300 images. The resulting images from the object detection and shape recognition algorithms are roughly anywhere between 70 by 70 pixels to 100 by 100 pixels in the resolution. The color recognition algorithm is able to accurately detect 8 out of 10 competition colors. When used in the best case simulation tests using 3 fonts with each degree rotation of an alphanumeric character for a font, the alphanumeric recognition algorithm yielded 99.3% accuracy. There are issues with the clarity of the images taken by the drone's camera, and to help mitigate this issue, the ODCL algorithms were also trained with blurry images. Low-density foam is added to the camera and its mount to help minimize vibrations and to take clearer images. The air delivery subsystem has been testing the airdrop mechanism to see if it is functioning properly. 30 tests were performed with a single component of the airdrop mechanism. This single component holds one water bottle. Each test was conducted to examine the time, accuracy, and speed of the mechanism. Out of a total of 30 tests, only 3 tests failed. The data collection shows a 90% success rate with the dropping parts of the mechanism. To prevent the line from getting tangled, a Velcro strap was attached to the water bottle to hold the line. This new configuration was tested 5 times with a 100% success rate. Further testing is required to fully get a grasp of how the air delivery subsystem should proceed further down the line. A 2-minute and 30-second communication performance test was conducted from a distance of 300 feet away from the safety pilot. During this test flight, 8,000 packets were sent, but 767 of them were lost, resulting in a packet loss rate of 9.6%. In the same test, throughput during flight remained between 1,000 and 2,000 bytes per second. Throughput for the manual control link is 50 Hz. The data transfer Python script has the following components: triggering the camera, geotagging images, and transferring image data to the Mission Planner laptop. For the data transfer mechanism, the Raspberry Pi is connected to the PIC-SOC and controls the camera. The Mission Planner laptop communicates with the Raspberry Pi through the corresponding Holy Row SIC 433 MHz telemetry radios connected to the PIC-SOC. A Ubiquiti Bullet M5 is used to transfer image data from the Raspberry Pi to the Mission Planner laptop. Testing will be done in 4 phases, with each component being tested separately and then as a whole. The following minimum requirements for UAS flight performance are: fly 12 miles at fully loaded in a single flight, fly a waypoint with a max area of 25 feet, and the threshold must be configured in the autopilot, turn radius of 150 feet, and be able to stay within the mission flight boundary. Angle of climb and angle of descent set to 20 degrees. Stay above 75 above ground level when more than 200 feet away from the runway. For vertical takeoff and landing, be able to use a runway approximately 70 feet by 75 feet. For horizontal takeoff and landing, be able to use a runway approximately 70 feet by 600 feet. To test the performance of the quadcopter, various flight tests will be performed with different parameters. During one of the flight tests, a full mission simulation was completed, which included flying 10 miles of waypoint navigation with errors of less than 10 feet, which was configured in UAV's software waypoint.py script. Since the drone is a multi-rotor, this allows for some of the minimum flight performance requirements to be easily completed, this being the turn radius, angle of climb, and angle of descent requirements. Furthermore, flight testing showed that the quadcopter was able to vertically take off and land consistently, easily capable of using a runway of 75 by 70 feet. To simulate the competition, the team will conduct full mission flight tests consisting of setup, takeoff, waypoint navigation, object detection, classification and localization, air delivery, and landing. Pre-flight setup involves attaching the batteries onto the UAV, plugging in the batteries, connecting to Mission Planner, connecting to the RC transmitters, verifying normal accelerometer behavior. Tilt UAV artificial horizon should respond accordingly. Verify normal compass behavior, verify adequate GPS signal, and set up the UAV in the runway for takeoff. By using the Mission Planner simulation, we can observe the accuracy of the drone's flight path. These waypoints and paths will be then measured by Google Earth Pro. Google Earth Pro will analyze the path is within 15 feet of range of each waypoint. We have conducted 35 software-in-the-loop simulations and have met all waypoints with no path going over the 15-foot range. Within these software-in-the-loop simulations, we also have included actions within the waypoint files to mimic a camera triggering for every X distance and a triggering a servo while loitering for 10 seconds at a waypoint to simulate a payload delivery. Since a simulation is not enough to measure the accuracy of the drone's waypoint path, we also have conducted physical testing. Our first physical test was conducted at the local RC field. Here we tested the waypoint file and observed the drone's flight path, and if it accurately followed the set waypoints. Integrating with the UAV subsystem was essential to test the air delivery system. The air delivery box was attached to the underside of the drone and flown throughout the nearest RC airfield to perform the autonomous payload delivery tests. While the overall test was relatively successful, there were a few glaring errors that had to be addressed. Some of the adhesive holding the box together separated, but it did not impact the results of the test. On the first drop, the Velcro that was used to hold onto the water bottles was too loose, causing the water bottle to slip out and hit the ground. And the damage from hitting the ground destroyed the water bottle. The following drops, while successful, raised concerns about the length of the line, which could affect whether or not the payload can fall from a safe height. Finally, some of the screws holding the spools in place came undone during the testing. To combat this, anti-vibration nuts were added to the system. Through the onboard computer, camera, and bullet radio, pictures embedded with the drone sensor data will be streamed on the ground station laptop. A script will be running to check for incoming images and autonomously process them through a series of algorithms. The locations and classifications of unique targets will be stored. During the setup, the target classification on the payload label and which dock it will be loaded into will be inputted into the script. These setup inputs and data gathered from the algorithms will be input through a waypoint creation script to create an air delivery waypoint file. To summarize, the dropping portion of the mission is crucial to the team's success in the competition. At this time, the success that were achieved during the design process have been promising. Testing and modifications will continue to better equip the drop mechanism for the best performance possible. The object detection, classification, and localization and data transfer systems are necessary for determining where to deliver the payload. Image processing will continue to train the ODCO algorithm with more data and improve their accuracy and speed, in addition to that of the drone's data transfer system.
And thank you for watching UHDT's Technical Design and Flight Readiness Review.
Recording good.